actually now we know that we have hosted many speakers and many young talents on this stage. So we're glad to welcome everyone on this stage and talking to Alice Zhang was Beijing now is this is different from the 4 years at one. That time was everyone was blocking home was dark days, black days, but now it's sunny days. As flowers, everything. I feel so excited and today we have a big party for the molecular electronics. This actually was organized by Philip of Hong Kong. Have a speaker from Hong Kong. Oh, sorry. Yeah, we have a speakers from national. We have speakers from Swansea, the UK. So we have a panelist from UK and from Hong Kong in Guangzhou, and also have me. So this will be an exciting event today. So let me first welcome our first speaker. As Philip Zhou. Actually, Philip Zhou, I met him, maybe 1 month ago, 1 month ago. Oh, not that long, but I feel very surprised. Looks so young, but already done so many outstanding works. Philip was got a BS from college, got the uh, got the PhD Cambridge, all in physics. I have a question. So all in physics, guy is doing a lot of work in electronics, famous, and got many awards, got many funding. I mean, Hong Kong, I heard that also funded young scientists, the young professors. And so he was a EPSRC doctorate 2010 and GSPS postdocs research fellowship 2006 and the Hong Kong RGC. It was SFC excellent young scientist, big all young scientists. It's not easy because he started his year how hard work. So Philip, please share your stories.
Thank you very much. I'll share my screen.
Yes.
Okay, so first of all, big thank you to Alice for the very kind introduction. So my name is Philip Chow from the University of Hong Kong. The topic of my talk today is mechanisms behind efficient and stable polymer solar cells. So basically, in light of climate change and fossil fuel, the fact that we need to reduce the use of fossil fuels, right? So solar cells are very important technology. Currently, we rely on inorganic semiconductors, such as silicon, for making our PV cells. Now, the issue with using silicon cells is that, first of all, they require rather high temperature processing, which means that they take quite a lot of energy in order to make a device, right? So when we start to run out of fossil fuels more and more, then basically we don't really want to afford, right, using so much energy or investing so much energy in the first place into making a solar panel, right? So basically, this is a major issue. There are other issues as well. For example, silicon panels, they're not transparent, right? They're opaque. They're not flexible, and also they're not biodegradable. So being opaque and not flexible also greatly reduces the capacity for installation in big city areas, such as London, Hong Kong, Shanghai, etc., right? So, but there are obviously advantages, right? They are very efficient and they're very stable, and the whole manufacturing process is already very established. The cost is also not that high anymore, right? But these are the main issues that we have to address. So this is also where molecular semiconductors or polymer semiconductors have a unique contribution. Um, Now, over the years, a lot of research has gone into making use of molecular semiconductors, which are basically synthetic materials made in the lab, which are mostly made of carbon, hydrogen, and other heteroatoms such as nitrogen, sulfur, fluoride, etc. Right? So these are, basically carbon-based materials that are also used in biological systems, and they can be synthesized in our laboratories, and we can have a lot of freedom in terms of how we want to design our materials. Um, so obviously, these materials are already used in light-emitting diodes, which, if you have a flexible, a cell phone which can be folded, then very likely the display monitor comprises organic molecules for light emission purpose. But basically, it is a light emitting diode, right? If you flip the operation around, instead of injecting electrons and holes to emit light, if you reverse the operation, then basically you can design a cell that absorbs sunlight and it can give you electricity coming out. And that is basically a solar cell, right? So in terms of the contribution of molecular semiconductors in solar cells, there are two versions, right? The first one is basically the whole active layer is made of organic materials, so polymers and molecules, and we can call them, all organic PV cells. So these are, they require very low temperature processing. So that solves the first issue, right? They're also semi-transparent, they're flexible, they can be printed, and also biodegradable. The issue is that they suffer from, more recombination processes. Historically, they are not efficient at all. But actually now the efficiencies are growing day by day, and we are now already approaching 19%. So a lot of my talk today will be focusing on why these materials can now achieve such high efficiencies. Make them, more or less comparable to the inorganic commercialized products. Stability is another issue that I'll briefly touch upon towards the end of our talk today. Now, a lot of you will probably have heard of perovskites solar cells. So in perovskites, the reason why they're hybrid is because they're also, they also contain organic molecules. But essentially, it's hybrid because it's half inorganic and half organic. And this is obviously a really promising technology as well. With basically they are also low temperature processing, semi-transparent, flexible, printed. And also, more importantly, they can already achieve very high efficiencies. But there are also some issues that, technical issues that we need to overcome, such as toxicity to do with the lead content, and also stability is another issue. But as I said, today I'll focus on talking about the all organic PV cells. Okay, as I introduced, it's not a new topic. We have been working on this for many years now. But you can see that, starting from year 2000, the cell efficiency of all organic photovoltaics used to be pretty low, right? Way below 5%. And gradually, step by step, we managed to increase the performance. In the year, 2012, we first managed to achieve like over 10%. And then, more or less, there was a plateau, for maybe 5 to 6 years where there wasn't really that much improvement. But clearly, you can see that, starting from 2018, suddenly we managed to find the magic ingredients, right, which enabled this really rapid improvement in efficiencies. So, hopefully this gives an overview, right? And now we're already higher than this number, right? Today, we're already approaching 20%. So basically, 20% is basically what, commercial inorganic cells can achieve. And what we believe is that now that we can finally achieve 20%, hopefully we can, continue the momentum and really make this, OPV technology into a commercial viable product. So for my talk today, I'll focus on two topics. The first one is about focusing on the charge generation mechanism in these high performance OPV materials. And secondly, we'll also discuss, the fact that right now we can achieve very high efficiencies. But the truth is that these high efficiency materials, they're also not completely stable, meaning that if you expose them under sunlight, they will actually drop in performance rather quickly. So addressing this instability issue is also equally important. All right, so now the difference between inorganic and organic semiconductors in terms of solar cell operation is that in an inorganic material, due to the high dielectric screening and the weak electron-phonon coupling, basically when light is being absorbed, so you promote an electron from the ground state to the excited state, the electron can very much separate from the hole left in the valence band relatively easily. And what that really means is that, an exciton is the electron hole pair that you generate upon photoexcitation. And this exciton in inorganic materials, they have rather low binding energy. So they can very readily separate as long as you give it some thermal energy, and they can separate. Now, when this condition is met, then basically all you need to do to make a relatively efficient solar cell is to develop this bilayer structure with a p doping and n doping on either side. And with this p-n junction, you can very readily separate the electrons and the holes and achieve a efficient solar cell with rather low, open circuit voltage losses. Now, the organic material is very different. Due to the low dielectric screening and strong vibronic coupling, the electron hole pairs cannot separate normally, right? They cannot separate readily. And in fact, they have rather high binding energies. And also, because of this binding, they also tend to have rather short diffusion lengths. Okay, so they cannot travel more than a few tens of nanometers before they release their energy and go back to the ground state, and that leads to energy loss. So it's because of this condition that to make an organic solar cell, we need to rely on this structural morphology. Okay, we need to blend in a mixture of p-type and n-type organic materials, and they cannot be like a simple bilayer structure, but instead they need to intermix a lot into this so-called bulk heterojunction structural morphology, where the domain sizes are comparable to the exciton diffusion lengths. Okay, so that all the excitons generated before they die away, they can always diffuse towards an interface, 20, 30 nanometers within where they're born, so that they can reach this donor acceptor interface, right, and be able to separate into free charges. Now, historically, at the donor acceptor interface, we need to engineer this really large driving force, okay, in order for the electron to efficiently separate away from the hole, okay, so that we can overcome this exciton binding energy. And this is exactly the reason why before 2016, where we were relying on a type of molecule known as the fullerene to act as an electron acceptor material. And whenever we use fullerenes, we basically need to have this really large energy offset at the donor acceptor interface in order to separate the electron from the hole. And it is because of this reason, right? Because we need to pay this energy deficit in order to separate the charges, that the efficiency has never been above 10% when we rely on these traditional materials. So clearly, right, you might be wondering, so how come now we can achieve close to 18 to 19%? And in fact, if you look at the energetics, what we find is that now we no longer need to have this really large energy driving force at the interface in order to separate the electrons from the holes. And we can see that using very sensitive absorption measurements and electroluminescence measurements. Basically, the result tells us that there's no longer this low energy interfacial charge transfer state, which we used to see for the fullerenes, but nowadays we don't see this anymore for the non-fullerenes. So what is the underlying mechanism, right? We understand basically it's the fact that we managed to get rid of this energy offset that enable this massive efficient improvement. But how come, right? We're still relying on carbon-based materials. How come nowadays we no longer need this large energy driving force? So in order to understand what's going on, the experimental technique that we use is known as ultrafast spectroscopy or ultrafast transient absorption spectroscopy, to be exact. So basically what this means is that electron separation process happens at really quick time scale. And by quick, I mean sub-picosecond time scale, right? So really, really fast times. So in order to really track what these electrons are going through as they separate, we need to make use of laser pulses, which are equally fast. So it's almost like taking a video, right? In order to observe really fast moving objects, we need to have a very quick frame rate, right? So this is exactly the reason why to track these really fast electronic processes, we have to use really fast laser pulses. Now, by doing so, right, we can then apply this technique to look at a variety of different materials. And traditionally, if we look at fullerene-based organic PVs, right, which are not very efficient, right, but historically what we had, we basically see ultra-fast charge separation, right? Electron and hole pairs, once they reach an interface, they can separate within 100 femtoseconds, okay, super fast time scale. And essentially, there's very weak temperature effects. But as I said already, right, because you have this, you engineer this large energy offset at the interface, you also end up losing a lot of energy during this charge separation process. So this is the mechanism of the old version. So then we apply this similar technique to look at the state-of-the-art high performance organic solar cell materials based on non-fullerene acceptors. And essentially, all of these materials have very small donor acceptor energy offsets. And what we find is that if we track the electron hole separation, as a function of time, then basically what we see is that first of all, the electron hole separation process happens at a much slower time scale. So before it was like 100 femtoseconds, right? But now we actually see this to be almost 1,000 times slower. In fact, it takes all the way up to 100 picoseconds to fully complete. So we now understand one thing, it happens a lot slower. If we vary the temperature, we also see a drop in the separation rate. So this also tells us something new, right? It now requires thermal energy in order to separate, or we can also call this an endothermic process. Now, obviously, a natural question is whether or not, maybe the exciton diffusion, right? I told you that exciton diffusion is also important. Maybe when we decrease the temperature, we're just modifying the diffusion rate, right? Which is also a thermodependent process. Now, we also did a lot of experiments where we changed the blending ratio between the donor and acceptor, which enables us to control the domain sizes, right? And basically, we for all the samples, right, even with very, very small domain sizes, we also see this temperature dependence, right? So that gives us an indication that maybe this, it is the interfacial charge separation that is indeed both slow and also temperature dependent. So, we kind of had from the data that I just described, we now kind of understand, right? When upon light absorption, we create, this tightly bound electron hole pairs known as excitons. These excitons, before they recombine, as long as they can reach an interface, which is 20 nanometers apart from where they are initially created, they can form, they can separate, and then they can then further separate upon thermal activation into free electrons and holes, right? So we kind of understand, this process, but there's still a question, right? what is exactly the nature or the property of the interfacial charge transfer state, right? Does it exist, or does it separate very quickly, right? So we still don't have this information. And essentially, the reason why it is very difficult to keep track of this interfacial state is because they look very similar to the free electrons, because they're both polarons, right? So in a standard transient absorption experiment, it's very difficult to differentiate these interfacial trap states from the other separated charges. So here, in order to shed lights on this question, we basically made use of an experimental method known as pump push probe electroabsorption. So besides the pump and the push pulse, we also introduced an extra push pulse that is only sensitive to the CT states. And this is obviously quite a complex experiment, but we did a lot of control experiments to make sure that we know the push does not affect the charges, the free charges, and it doesn't affect the excitons. So they would only interact with the buried or the trapped CT states buried at the interface. So using this method, we were able to get direct evidence that these states do exist. And in fact, these states live for a long time. Okay, we first managed to see that these states have a lifetime way longer than 100 picoseconds. Now, essentially, this separation rate takes 100 picoseconds, but the fact that we are seeing a lot of them, even beyond 100 picoseconds, also tells us that once they thermally separate, upon recapture of the electrons and holes, they can actually repopulate this state. So essentially, what we have is an equilibrium that is being established between the CT state at the interface and the thermally separated free charges. So we have this first direct evidence that is, and the excitons and the CT states, the free charges, they reach an equilibrium. And furthermore, right, if we look at the delayed time correlated photoluminescence, what we found was that excitons, the emission from exciton states can go all the way beyond a nanosecond timescale. So basically, what we have is that we have all three states which are in a steady state. Essentially, once we form CT states, they can either go this way, but they can also, they're also hybridized with the exciton state, such that the energy can be exchanged back to the emissive exciton state as well. So this is what we found, and it was published a few years ago. But basically the important point is that in the traditional materials we have ultra fast charge separation, and that was what we always believed. If we want to design an efficient organic solar cell, we must engineer a process to rapidly pull away the electron from the hole. Otherwise, we cannot achieve high efficiency. But essentially, what we have now found is quite the opposite. In the best performing organic solar cell materials, the charge separation doesn't need to be ultra fast. In fact, it's relatively slow. It happens on a tens of picosecond time scale, and it's very much a thermally activated process. So obviously, now we kind of understand what's going on. We also need to relate it back to the molecular design, right? So one thing is that because of this process, we learned that the excitons must have a very long exciton lifetime in a nanosecond timescale in order for these states to gradually separate. Okay, so this result was actually what we also found in the best organic solar cell material right now is known as Y6. And we do indeed measure a very long exciton lifetime. And this result is very much consistent with what Professor Brabeck has found as well, and published roughly at the same time. We also think about, so how, now that we know the CT states live for a long time, right? So what is the condition for them to separate so slowly, right? So lifetime is one. But actually, we also find that the exciton wave function delocalization happening at the interface is also very important because that enables the binding energy to reduce quite substantially. Okay, so we found that it dropped to about 0.1 electron volts, and we very much believe that this is a reason why we can now have this efficient and slow endothermic charge separation going on. And obviously, Mike with Justin has also did a lot of work on these materials. Yeah, we can discuss more in the panel discussion. Now, in the remaining 8 minutes or so, I'll just quickly go through the second part of the talk, which is about instability. Now we have pretty efficient organic solar cell materials now, but as I said, right, so the materials they have really low miscibility, okay, between the donor and acceptor material. This is actually the reason why we have these really highly pure domains, okay, which are often believed to be very good for efficiency. However, if you have this low miscibility, what happens is that thermodynamically speaking, the two materials are actually not in a stable structural phase. Okay, essentially, if you give it a bit of energy, right, which you will under sunlight, they will over time they will decompose. Okay, and you lose this morphology. So this is well known. But at the same time, recently, researchers have also found that if we polymerize the acceptor molecule, right? So instead of just having one molecule, we now have some interlinks, and we extend the chain to 6 to 8 repeating units or even longer. Empirically, we found that the stability of the blend becomes better. Okay, device efficiency becomes better. But what is the underlying charge generation mechanism? Okay, so there's the next question that we try to solve. So again, introducing transient absorption spectroscopy, we basically first looked at the charge generation timescale in the blend system. So this is the control sample, PM6Y6, the small molecule acceptor, and this is PYIT, which is a polymerized Y6 molecule. The first information that we got was that charge separation happens on a very comparable timescale. They're both very slow and also both temperature dependent. So this gives us an indication that indeed we have just the same charge separation mechanism going on. And remember, I just told you, right? Since it is happening so slowly, we need to have very long exciton lifetimes, okay, in order for this slow separation to be efficient. Now, surprisingly, we studied the exciton lifetime of these materials in films, and we actually find that unlike Y6, we actually get relatively short exciton lifetimes for these polymerized acceptors. And that was quite puzzling, right? If they live for only a short time, then how can we have such efficient, slow separation? So interestingly, right, what we found was that, in the pure film, they do have very short lifetimes. But as we disperse them in a solution, either a solution or in an insulating polymer matrix, we find that the lifetime of the exciton is very much aggregation dependent. So basically, if they all crumble together in aggregates, then the excitons have very short lifetime, and they would not be able to separate efficiently in the blend. But if they are efficiently dispersed, they can actually have much longer lifetimes, which will satisfy the condition for efficient endothermic charge separation. So then that leads us to think, right? Do the polymer Y6 materials, are they really dispersed at the donor-acceptor interface? So to find out, we collaborated with Professor Yi from Beijing. What we found was that using molecular dynamic simulation, indeed, in the all polymer blends, there's a higher average donor-acceptor contacting atoms compared to the small molecule counterpart. We also find that the PM6 are a lot more curved and the PYITs are a lot more stretched. So, these are basically fancy quantitative terms to describe that. What we find is that when we polymerize the Y6 acceptors, the donor acceptor miscibility is improved. Okay, so that would enable them to form this interlocking morphology or intermixing, right, at the interface. We also did resonant soft X-ray scattering to get experimental results to verify this. And indeed, compared to the control Y6 sample, we find a decreased domain purity in these polymerized versions. So again, indicating we have a greater donor-acceptor admissibility and increased donor-acceptor mixing at the interface. So that brings us to consider the structural property relationship of these polymerized versions of the acceptors. Essentially, in the Y6 traditional material, they are basically hypomiscible because they have very low miscibility. There's very almost no mixing at the interface. But when we polymerize them, there's increased miscibility, enables us to form this donor-acceptor percolation network at the interface. So this, structure actually serves two purposes. The first is that, remember, when we disperse the polymer chains, they can greatly, the exciton lifetime is greatly enhanced. So this firstly satisfies the condition for the efficient and slow charge separation, enabling the electrons to gradually separate upon thermal activation at the interface. But at the same time, this also brings this structure much closer to the so-called, thermodynamic stable phase. Okay, and in fact, this is the reason why the device stability is also improved when we polymerize the Y6 acceptors. Okay, and we see this in experimental data. But a note is that the reduced domain purity and the crystallinity may also may also help us explain why the charge transport performance may also be slightly reduced in these materials. And we can see that from the device parameters where the fill factor is dropped a little bit, and that's why the power conversion efficiency is not 19% at the moment, but 17% or so. So, basically there's a trade-off between efficiency and stability. And I believe that, this is probably the greatest challenge that, we face right now in organic PV research. So now we have an understanding of how the charges separate, the time scale, and whether or not temperature matters. They are very different to the traditional fullerene types. We no longer need to physically pull apart the electron from the hole on an ultra-fast time scale. Um, uh, you know, uh, by which will also lead to a lower open circuit voltage. But now instead we will we can harness thermal energy and enable the electrons and the holes to separate quite gradually, okay, slowly but gradually, but without needing to lose any energy at the interface. So in the long run, this is why we now have more efficient systems. But then we now have the stability issue that we need to solve together. And we need to find a way to both stabilize the donor-acceptor interface, the overall morphology, but at the same time without compromising the charge transport and due to the reduced purity of the domains and the crystallinity. So this is maybe I'll just finish here. So hopefully that's an overview of OPV research over the past few years and the current challenges that remains to be solved. So thank you very much for your attention. Just acknowledge my students, my collaborators, my funding, and thank you for your attention.
Okay, super. Yeah, a great talk available. Every time you enjoy a talk very much. And yeah, today I'm thinking, yeah, Kang, you just later, so we sweep you speaker. Okay, now we go with Evans. Actually, Evans was the last place. Swansea. I mean, there were a lot of fans. Yeah, I love that. The professor in the Emrys, Evans, doing a lot of work, materials. He got degrees with chemistry and Oxford. So Philip was in physics and in chemistry. You now is molecular electronics, and his wonderful professors had friends. Haven't do laboratory that's really a lot of now we know Emrys. Yeah, from there, yeah, he began to factors electron. He raised their work and 2021 he added STM steams. Steam. Normally it's STMS, now it's STMM. Then the Society of it really published language special. Why? That's really, yeah, Evans. Are you deliver your talk in Thai or in Chinese?
I'm going to deliver in English today,
Please.
but yeah, we can do a bit of Welsh and Thai later. Yeah, why not?
Sure.
Thank you so much for the introduction, and it's a real pleasure to be part of this. So thank you, Philip, for coordinating as well this opportunity. So I'm just sharing my screen now. Hopefully that's come up. So today I'm going to talk about exploiting exciton and spin dynamics in molecular materials. And I'm going to tell you a bit about some research stories to do with this molecule that I've drawn on the beach here in Swansea. It's another sunny day here today as I give this talk. So it looks a bit like this today. So I want to talk today about some of the work that we've been doing on light emitting materials in devices that work in the opposite sense, I suppose, to what Philip was talking about in terms of solar cells. So this is a schematic of how molecules can be used in light emitting devices. And it's a story in which it's been a really classical example of where electron spin properties has been really important. If you take a material which has a kind of classical electron configuration like this, where electrons are filled up to the HOMO and unfilled from the LUMO, with a singlet ground state, on electrical excitation, you form singlet excitons 25% of the time and triplet excitons 75% of the time. And as I set out, I suppose in my abstract, what I kind of wanted to put across was that in molecules, the spin of your ground state and your excited state really dictates what photophysics can happen. And in our case, if we were interested in making a light emitting material, we try to match up the spin of your ground and your excited state so that you get more efficient radiative transitions. And for molecules with a singlet ground state, because you form this singlet exciton 25% of the time, you have to put some work in to get the 75% triplet excitons to work for you. This has been sorted out to some extent in industry. So one method is to take a delayed fluorescence process called triplet annihilation that converts two triplets to one emissive singlet exciton, in which case you can recover some efficiency. Something else you can do is to try to promote phosphorescent emission from the triplet excitons. This is also something that people are employing in industry, especially for red and green colors, and this works pretty well. And over the last decade or so, there's been a push to finding ways in which you could convert more efficient emission from triplet states through thermally activated delayed fluorescence, or this is E-type delayed fluorescence. And there's an interest in this area in particular because there's a long-standing issue of getting blue efficient OLEDs to work. And this is extremely important because they're kind of making the back end of kind of state-of-the-art displays, and is how companies like Samsung are kind of pushing this forward at the moment. So having given you a little bit of a background, today what I want to cover is some of our work on using organic radicals as luminescent materials and how we're exploiting these in efficient organic light emitting diodes, trying to change the spin playground of your ground state and your excited states. And finally, some work that we've been doing on trying to couple strong light interactions to the magnetic properties of these radicals. So this work actually something that I started working on when I was a postdoc with Richard Friend in Cambridge, and has been part of a really fruitful collaboration with Feng Li at Jilin University, and it was a great pleasure to meet him those years ago, and we've had a kind of a great time working together since then. So let me start by telling you about radicals as luminescent materials. And what I wanted to do was to draw some of the kind of critical developments that have happened in the field. And you'll notice that the star materials are based on this triphenyl methyl radical motif in which it's chlorinated. And it was I suppose the invention and the discovery of Julia Lopez who put a hole transporting material onto this material that really unlocked efficient luminescence. Later, Christoph Lambert and Tetsuro Kusamoto also derived efficient luminescent radicals based on similar motifs. And it was Feng Li who was the first to put these into efficient OLEDs. So what I want you to kind of take away from this picture is that most of the materials that we have to play around with really are using this triphenyl methyl radical motif. And something else that you might notice is that a lot of the materials that work well are combining this radical with electron-rich or hole-transporting materials like the carbazole and the triphenylamine, which is something that we'll come back to in a little bit. So to orient you about these materials, if you think about them, a radical is a material where you've got an unpaired electron that sits in a singly occupied molecular orbital, and it sits between your HOMO and your LUMO. Now, we call them doublet materials because in the ground state, the electron can be spin up or spin down. And to now kind of build up the spin playground of these materials, if you want to think about how you can excite it, you can imagine a transition from a HOMO to the SOMO to create the D1 excited state. You could also imagine promoting electron from the HOMO to the LUMO. And if the electrons are aligned in this configuration, you form quartet states. So whereas before we had singlets and triplet states formed in non-radical, more conventional materials, in our systems, we have doublet and quartet states. Why are these potentially useful is that if you now imagine running these in an organic light emitting diode, in principle, you can go from a doublet ground state to purely doublet electronic excitations. And now in these materials, actually, your lowest energy excited state is bright and luminescent. You can get fluorescent transitions from these systems. And in principle, you totally avoid this singlet triplet spin statistics problem. So far, so good. To get this to work, what you really need is a luminescent radical material. And this was something that we were very fortunate to be provided with by Feng Li in 2018, is this example of the TTM3NCZ molecule. And what I wanted to show you here is that this material is an excellent near-infrared emitter. It has a photoluminescence quantum yield of 86% in films, or 50% or so, or 49% in solution. And what you can see here is that this efficient luminescence actually happens on tens of nanosecond timescales. So this is the Emrys photoluminescence plot on the right-hand side. So this is an excellent property for organic light emitting diodes, because basically if you can have an emitter that emits rapidly on nanosecond timescales without this spin problem, in principle, the quicker you can get your light out of the device, the less time there is for something to go wrong. To tell you a little bit about this material and how to think about it, so this radical, when it's combined with hole transporting materials, acts a bit like an electron acceptor. So when you photoexcite this material and you put it into more polar solvents, it actually just undergoes a strong solvatochromic shift as it redshifts the emission, something that you expect in a sort of charge transfer type or electron donor acceptor type dye. So something that I wanted to kind of pull up and orient you whilst we're thinking about these materials as light emitting materials is to kind of highlight how come it took a while actually for this area to pick up. And that's because the parent molecule itself is not very luminescent. We did some work a few years ago to try and understand why this was the case. And we uncovered some old ideas by Coulson Rushbrook who looked at the symmetry of these molecules and worked out that actually this singly occupied molecular orbital sits midway between the HOMO and the LUMO in such a way that you can use this to try and explain why you get weak light absorption properties, which mirrors into a slow radiative rate. This was brilliant work done by Tim Heal, who's a theoretician at University College London. And what he recognized by going through the quantum chemistry of this is that actually, if you have this midway singly occupied molecular orbital, and I try to draw an electronic transition, that's the lowest excited state, I actually have to take combinations of HOMO to SOMO and SOMO to LUMO transitions. And actually, the lowest energy absorption happens through an outer phase combination. So you have a weak oscillator strength and low radiative rate. So in our materials, actually, by employing this Hall transporting material that creates this push-pull character, it not only creates a different type of emission, but actually, importantly, it breaks this electronic symmetry property and allows you to have luminescent materials. So does it work in a useful way for devices? So that's what I want to tell you about next. So I've shown you that they can be used as luminescent materials. And actually, yeah, something that we did a few years ago was to try to take this understanding and use chemical modifications to tune the color of these materials. So straightforwardly, we could take nitrogen substitutions of the carbazole group to tune the emission properties a bit. So depending on where the wave function of this carbazole had and where you put the electronegative group, you could tune your emission. And we could match very well the coordinates that you need for a red device. And what I want to draw your attention to in these organic light-emitting diodes is that the efficiency that we can reach, at least at the low current density, is above 10% still quantum efficiency, which means that we're getting around this spin statistics problem. But it's true that actually, as you run these devices to higher voltage and higher current density, the efficiency drops off, which was something that we didn't really expect, given that, as I told you before, these materials were efficient in luminescence and they emit on fast timescales. In principle, you don't tend to have this drop off in efficiency as you go up. And we think that this has got something to do with actually a different nature of charge recombination in how these devices work. And whereas the singly occupied molecular orbital sets up a useful manifold of doublet excited states for your radiative transition, it also introduces a problem in which that electrons and holes can also recombine at this state. So something that you have to do is to engineer your devices to make electron and hole recombination happen in the right way, let's say. And that's something that hit us in terms of the performance of our devices. And a few years ago, we started to play around with energy transfer devices in which we took the charge recombination event away from the radical, which was posing some problems for us. And we did this here with actually a sort of fruit fly material for the organic emitter community, which is 4CZ-IPN, which has been very well studied for thermally activated delayed fluorescence materials. And what we were able to do actually is to take this concept of a sensitizer that transfers to a terminal emitter that is used in the TADF community and actually show some benefits of doing that with radicals. Because whereas in most materials you would have a low-lying dark trap state, in these materials we were able to show that you could get efficient direct triplet transfer from this triplet state to this luminescent radical state. This is actually a bit of a game changer, really, because now you can directly exploit excitons from triplets to doublets. And we've been able to employ this recently to really push the performance of near-infrared devices using this material here, another radical dye with another TTM with a Hall transporting material, here combined with this anthracene derivative used as the host. And here I'm showing you the emission properties. So we lined them up for energy transfer. And what we could find when we monitored the transient absorption spectroscopy, as Philip described in the previous talk, is that in these systems, we can get very efficient transfer from singlet excitons to doublet excitons through a Forster resonance type mechanism. And also through monitoring the time resolved photoluminescence, we could see that we set up efficient radical luminescence when we excite the MADN. But let me draw your attention to this delayed plot. So if you can see that there's this hump in the luminescence, which showed you that there's a delayed emission as the system sets up an equilibrium between triplet and doublet excitons. And this happens whether or not you excite directly from the host, or in this case, also through the radicals. So actually setting up this device structure in which the triplet is resonant with the doublet is really allowing us to push the boundaries of performance that we see in near-infrared OLEDs. And actually, if we compare that to the current literature, we can really push the performance from 5% external quantum efficiency to way beyond 800 nanometers. And the way this works actually is that you can get a spin-allowed triplet to doublet transfer, which happens through this doublet channel. And I've shown here the combination of triplets and doublets that happen in an allowed way for transfer. But equally, actually, when triplets and doublets come together, you form not only doublet states, but also quartet states, which is something I want to tell you a bit about the next part of my talk. Because these quartet states actually are key players in how we can use these materials as potential quantum objects in which we can use a spin optical interface to couple light to magnetic states. So we'll switch gears a little bit now from optoelectronics to molecules as quantum systems, and to tell you a little bit about how you can combine organic radicals in triplet states. And if they are aligned all in the same direction, you can form these overall quartet states. And if they are formed in a sort of anti-parallel configuration, you form overall doublet states. You can kind of watch this through how the electrons point up and down. And this is an area that's kind of re-emerged in interest recently as people are exploring potential opportunities for using molecules as qubits. And this is really credited to Sabine Richert and Mike Wojciechowski, who've been real pioneers in this field, in which they've taken chromophores, as shown here in blue, and combined them with radicals, as shown here in green. In these systems, they use non-luminescent radicals. And what they do is they photoexcite the chromophore, so the blue part of these molecules, to form singlet excitons, which then efficiently generate triplet excitons dressed up as overall doublet or quartet states due to this interaction with second radical. So in these systems, they create these high spin states, which are quartets, which are potentially useful for creating quantum sensors and other applications to detect electric and magnetic fields. So we were interested in seeing whether there were some opportunities to use our luminescent radical motif to improve some of the properties that you get from radical triplet systems. So we took our fruit fly molecule, which is TTM1CZ, which is a luminescent material with a spin doublet and 41% luminescence quantum yield, and we paired it simply with anthracene. And we chose this so that we could create energy resonance between the doublet exciton and the triplet exciton. We wanted to explore this potential for having equilibrium states and transfer between these high spin states. And what we noticed when we performed the transient absorption spectroscopy is that this system, if you track the doublet exciton, it rapidly decays on the same time scale as a feature that we can attribute to the triplet exciton on the anthracene comes in. This was quite surprising because actually, when we took this material, it still retained a high photoluminescence quantum yield. And that's because most of the emission actually comes out through this, or a significant amount of the emission comes out through a delayed channel. In fact, these materials, you can think of them as sort of radical thermally activated delayed fluorescence materials in which you can activate this delayed fluorescence. It has a 30 milli-electron volts energy. These systems, we can track them through optical spectroscopy, but to understand their spin properties, we have to use magnetic resonance techniques. And in magnetic resonance, when you apply a magnetic field, you create splittings between the energy substates, which you can probe through microwaves, and which you get characteristic signatures on whether your system is a spin 1 or a spin 3/2 or a triplet or a quartet state. So performing these experiments, actually, we could attribute our strong triplet signals in reality to being triplets which are coupled to radicals to form overall quartet states. And the phase of our signals actually inverted with time with an activation energy which exactly matched the optical spectroscopy, showing us that these magnetic properties were directly related to the optical properties that we saw in the system. So to summarize, what we're kind of seeing here is that whereas before people were exploring these the opportunity to create quartet high spin states through the non-radical chromophore, in our scheme we can directly photoexcite to a level which is degenerate with the triplet state in these materials to create high spin states through radical photoexcitation. And these systems not only intersystem cross to form quartet states, but they also reverse intersystem cross to form doublet states with efficient luminescence. This actually gives us an opportunity to use these quartet states for the first time for light-based spin readouts. So we can perform optically detected magnetic resonance and couple the doublet and quartet emission to the spin state of the system. And we are now using these systems to create building block quantum objects. So here, going from single radicals, we can also study biradicals, in which we can build up new Jablonski diagrams now with quintet, triplet, and singlet states. And the result in this system is that when we photoexcite the system, we efficiently form this quintet state, and it climbs back through the triplet channel, in which case you can imagine it as a little bit like a light switch. So you photoexcite the system, you form this high spin state, and then it returns back to the ground state with all of the electrons lined up in a spin polarized way, which is which was an exciting result for us at room temperature. I've got just a little bit of time, so I just wanted to kind of tell you finally some of the work that was recently published last week, as we're now trying to really dig into the opportunities to use these systems as quantum objects, and we're studying how we can use these as magnetic field sensors. So what I'm showing you here is that our approach is really to think of these materials as building blocks. So whether you've got your radical and your chromophore, and the interactions of the system are the electron exchange interaction between your radical and your triplet state, and also magnetic interactions that happen within your triplet exciton. Now, when you do that, you can start to understand how magnetic fields lead to crossing points between these levels, which you can study through magnetic field-dependent photoluminescence. And we can also look at how we can change the spin polarization state of our system. So to what end do we want to do this? Actually, what we're interested in doing is to explore the opportunity of using these building blocks as chemical compass systems, in which we can tune the light response of the system to the angle of a material with respect to a magnetic field. So with that, I'd like to thank you very much for your attention. Just to summarize, I've told you a bit about radicals as luminescent materials, as their opportunities in organic light-emitting diodes, and how we are looking at them now as opportunities to couple light and magnetic spin states in the materials. Thank you.
Okay, super. Emrys, you save the time. Oh, thank you very much. Yeah, always you get more questions after you talk. I think we save the question. Now, welcome. Keehoon. Yeah. can you
Hello.
share this? Yes, yeah. I'll give you a brief introduction, and you
Thank
can
you.
share your. So we did double check your slides just now, so
Sure.
please. Yeah. Professor Kang now is a professor and so national. There is a alumni from Cambridge, the BS, MS, and the two there. Went back to Korea as and so and in fact they started in lead one lab, number one lab, for organic next generation electronics, active and actors. He members of science fellow, young scientist prize, physics prize, awarded advisory. Yeah, Kang.
Alice, thank you so much for the introduction, and I'm sorry that I didn't join in for the 30 minutes early preparation. I was too confident that I will share my slides just on time, which I think I'm doing now, so everything's well. And thank you, Philip, for coordinating this wonderful opportunity. I've actually been in the past ICANN-X talks online, and I enjoyed the great learning opportunities in the past, and it's my pleasure to give a presentation here. And thank you for everyone listening, probably across the globe, I guess. So today I'm going to talk about our doping work in what are called emerging semiconductors, but mostly on metal halide perovskites. So we are switching the gear a little bit. So Alice did a great job introducing me, but I think it's always good to introduce myself. So as Alice said, I think I share with Emrys, Philip, and Mike. Also, I think Jiayang here on the experience of living in UK. So I did my long years of study in UK, working in the same group as Philip, Emrys, and Mike in the optoelectronics group. Except that I also worked with Richard a little bit, but mostly with my supervisor, Professor Henning Seringhaus. So I was mostly on the electronics side of the organic materials. And these two basically sum up my PhD research on the doping and charge transfer physics in conducting polymers, as well as some spintronics works, which have been heavily explored in the same group since then. And I thought I would expand in terms of my material scopes during my career, not just focusing on organics, but during my postdoc, I thought about, trying other materials as well. And metal perovskites has certainly formed a new avenue for exploring solution processed high performance materials. And I've since during my postdoc, I've worked on designing thin film processing by thermal evaporation of these perovskite films, as well as the light emitter synthesis, and how to use these films for high-performance electronic and ionic devices. And mostly today, I will talk about the doping of these materials, which is very challenging at the moment. And I have a unique background, I think, if I may say, of having explored these different transfer physics in organic, as well as the emerging semiconductor materials, and especially on the doping work. I've tried to develop efficient doping methods for not just organic semiconductors, but 2D materials, as well as metal halide perovskites, based on a large degree of freedom that the molecular dopants provide on these emerging semiconductors. So today I will talk about mostly about perovskites, but a little bit on the 2D materials as well. Let me start by saying that doping is essential. Philip touched on this during his talk about p-type and n-type doping, but if I just give you, I know this is not semiconductor physics 101, but it's always good to brush up on the idea of doping. So if people are familiar with the concept of doping, how this is achieved as well as this result, for silicon, which is group 4 atom, for a periodic lattice, what you do is you replace atomic, so you do an atomic substitution of silicon with group 5 or group 3 atom to n-type dope and p-type dope respectively. And due to the heterovalent atoms that are introduced into the lattice, you're gaining or losing an electron in this case. And therefore, the result of this process is that you get free carrier generation. And concurrently, what you say in terms of the electronic structure is that you create these impurity states that can be ionized to give you a free charge carrier concentration. Therefore, this results in the Fermi level shift. And if you know this equation from the undergraduate physics course, where the conductivity is related to how many free carriers you have in the system, as well as this charge times how fast they can move, you can immediately see the importance that by tuning this carrier density, you're able to tune the conductivity as well. And if I just sum up by these emerging class of materials as well as the devices that have been heavily explored in the field, including optoelectronics, stretchables, neuromorphics, all these different devices and also materials. If I pick out two most important transfer parameters, there would be the mobility as well as the carrier density, which are also included in this equation. Therefore, depending on what kind of devices you're looking at, what kind of materials you're using for target devices, you are exploring different regimes of transport. And it is important that you tune your doping level and use the right doping levels to target certain applications. And you can immediately see in this diverse range of materials that doping will be important. And if we go back to the fundamentals, it is, of course, used in creating a built-in field for LEDs and PVs, as well as bridging this hetero interface between metal electrodes to active channel by heavily doping the contact areas to reduce the ohmic losses. And therefore, this is directly related to the performance of your devices, as well as the power consumption are important. And this work of doping during my PhD, I had a taste of how doping can give you solutions for different device applications as well. So during my PhD, we were part of the team. I was part of the team where we developed an efficient molecular doping in conjugated polymers. And that actually resulted in a high conductive and also high doping level efficient doping method. And that could have been applied to thermoelectric devices, as well as the contact doping in organic FETs. I know Emrys talked about spins a little bit during my PhD. I also explored spin transport. And my friends, by using the same technique, doping technique, they were able to actually explore the long-range spin transport of these doped polymers. And if I may say, this doping method provided new methods for exploring other hundreds of works. So then generally, if we think about doping, what should we target in terms of making doping applicable as well as useful? First, you need to talk about the doping efficiency, and therefore you need to ask the question, how wide the doping level? Second, you need to have the controllability of the doping so that you are able to finely control for the target applications that you have, therefore how fine. Third, doping processability. You need to make it processable in order to make it more practically applicable for industry, for example. And there comes in the material introduction of perovskites. I'm sorry about this rough sketch of the introduction to metallic perovskites. And I know some of the panel members here have worked on this topic for a long time as well. If I just may say that it is named after a structure, ABX3 structure, where these octahedra are corner shed with each other to be extended if it's the 3D perovskite in the 3D form. It can be also 2D, 1D. Also, people use them for nanocrystals as well. And their main interesting properties lie in optoelectronic as well as the charge transfer properties, where their bonding is such that you are defect tolerant, and therefore you're creating states within the bandgap to tolerate the number of defects that you could have from, for example, halide vacancies. And I'm mostly interested in these charge transfer properties, which haven't been looked at so much relative to the optoelectronic properties, where it is expected that you have a very low effective mass for these materials, and therefore a very high mobility. Although this doesn't take account into the electron-phonon coupling, let's say, but people are expecting a large mobility that gives you a high device performance. And not to forget, these are also low energy processable materials. And if I may give you the motivation for why doping in perovskites would be important, it is also because of its cost factor. So if we talk about the mid-halide perovskites based solar cell module, large portion of its solar cell module, the cost for it is actually composed by the Hall transfer layer, for which like we use for OPVs as well. We use spiral ometard, which is considered to be very expensive. And since that is the dominant cost factor, we come to a question, okay, why can't we eliminate it and use something similar to PERC structure that's already used for commercial silicon solar cell? So if we dream that if we can dope perovskites efficiently such that we create this PN junction for perovskites to make a structure very simple and also less expensive, then there's an avenue for where the doping for perovskites can be very useful. Also, if I give you the Nobel Prize example, which is not directly related, but this Nobel Prize in 2014, when Nakamura et al. For gallium nitride for 3.5 LEDs. One of the critical challenges was actually to come up with an efficient way of p-type doping and therefore making PIN junction for gallium nitride LEDs. And therefore, I don't see there's too much difference in perovskites at the moment, where the blue LEDs are causing problem in terms of the efficiency as well as the stability. So if we can come up with some efficient p-type doping method for useful device applications, then that would be also a great contribution to the field. And lastly, if I talk about the processability of doping, from the literatures that I find, we know about ion implantation doping for silicon, where it's been established and people use it all the time, where you first use the thermal diffusion of these ions, and also then you accelerate these ions by electric field in order to spatially target where your ion dopants will be. So you have a way of spatially as well as in terms of the level and finally controlling your doping level via post-growth doping, meaning after you deposit film by using a fantastic method for PCVD, whatever, and then you are able to dope on the high-quality film. And for perovskites, unlike the silicon, for example, you have a way of, let's say, changing the precursor ratios by going non-stoichiometric and also mixing in with some dopants. But since that part is very complicated, also fiddly to get good films, high-quality good films of perovskites, there's a question of, okay, is there a post-growth doping method where it can be very useful? So if perovskites were commercialized, which is very getting near it, if we have a way of post-growth doping these films, then that will also be very industrially applicable. And next, I will talk about the electrical doping, different types, what have been tried in perovskites and what can be possible. First is the extrinsic doping, similar to the silicon type that I mentioned before, where you are replacing these ionic components with heterovalent other ions, where by substituting these ionic species, you are creating some defect states that can be ionized to give you free carriers. And there have been certainly a number of different elements that have been tried for perovskites, but as I will tell you later, not so efficient so far. Also, there's intrinsic doping, where you are creating, you're just using the fact that the defect formation energy for perovskites is quite low. On the contrary to what many people believe, that these perovskites defect tolerant, they are by properties, but there are defects because the formation energy is very low. For example, the halide vacancies, there are so many numbers of them, which can cause ion migration in the material, but they can create these defect states that can be ionized for creating charge pairs. The third type is more the charge transfer doping type, where you are using the physics dopant molecules, for example, where there can be charge transfer between the host semiconductor and the dopants, such that via these energetic driving force, you are trying to drive some electrons from host to the dopant, which will be p-type doping. Reverse will be n-type doping, vice versa. If you want to know more about this, there's this recent review that we wrote on doping and perovskites, so please have a read. And there are pros and cons with these doping types, especially the extrinsic doping, where since, as you can see, the structure of perovskites is quite restrictive in terms of allowing different types of elements that can fit in this geometrically restricted environment. You have limited structural stability for lots of elements, and there are also self-compensation effects, which I'll tell you, due to the loss of defects that are flying around. And that will compensate for any external impurities that we put in. And for intrinsic doping, if you're using so many of these vacancies, in the end, you're going to make your material very unstable. And therefore, there's a limited range of how you can use this intrinsic doping. Whereas the molecular doping, it's certainly via physical option, less destructive. Also, there's a large degree of freedoms for what you can use for molecular dopants for tuning the energetics and also the interface properties. But this is mostly limited to the interfaces. So for example, here, like the interface. So it is a question of how to incorporate as many dopants of these as possible to have a high level of doping for perovskites via molecular doping. As a side note, I would like to tell you that we've recently worked on this intrinsic doping, and we've systematically also directly seen this effect of reversible air-induced p-type doping into the perovskites, which has been recently published. So please have a read if you like. So molecular doping in perovskites. Why we need to work on this doping type is because the other doping types have been quite unimpressive in terms of what it can achieve in terms of doping level. So the majority carrier concentration is seen here for extrinsic type doping for bismuth 3+, which will be anti-doping. The range of conductivity or charge carrier concentration that can be tuned is only up to 2 orders of magnitude, for example, compared to, let's say, 6 or 7 orders of magnitude that silicon can achieve. It's very underrepresented. And also intrinsic defect type doping, as you can see, as mentioned before, you are constantly damaging the material. As the more the doping you induce by intrinsic defects, the mobility is decreasing, which is reflecting the fact that you're just damaging the material constantly. Whereas charge transfer doping has been explored for being used in perovskite solar cells for giving you better charge extraction. The range is limited because, as you can see here, the range is only from 2 to, let's say, 5, factor of 5 for nanocrystals. And we thought this was because this is only playing at the interface. So we tried to come up with an idea where we can achieve bulk molecular doping for perovskites. So basically, efficient molecular doping via bulk doping in perovskites. My next idea. And if I just tell you what I've been playing around in terms of the core concept in doping is similar to the modulation doping that's been used for high mobility, ultra high mobility 2-deck system for agar gas quantum well, where you are spatially separating, instead of uniformly doping the channel as well as the wall, you're only doping the inactive area of transport, and via energetic offset, you are diffusing in the charge carrier so that channel here is depleted of the ionized impurities, which will reduce the scattering effect. And therefore, you are preserving the mobility of the channel, via minimizing the charged impurity scattering by physically separating the dopants in the semiconductor. And I've tried to do that for the organic semiconductors, and there comes in my 2D work, where I thought, okay, this should be able to be done for 2D materials, where the hexagonal boron nitride gives you a very nice insulating spatial spacer for separating the charged dopant to the semiconductor, where we actually saw that the extent of charge impurity scattering was much less for this remotely charge transfer doped molybdenum disulfide channel. So how about for perovskites? So basically, as soon as I saw this 2D perovskite, where this octahedral network structure forms a layer for charge transport, and this is separated by layers with these organic spaces, bulk organic spaces. So it's a layered material, layer structure that you see. And depending on this number of octahedral layer, it can be n equals 1, n equals 2, n equals 3. They are all Rutherford-Popper type phase, for which we've structurally characterized by NMR. But as soon as I saw the structure, I thought, okay, as I mentioned before, this area of inactive transport maybe could be used for doping by remote charge transfer and preserve the channel layer accordingly. And the way we achieved this was very simple. So how we did this was basically using this strong molecular acceptor, magic blue, which can be dissolved in a particular solvent that does not dissolve perovskite film, so that via the solvent carrying these magic blue molecules, you're able to bulk incorporate by penetration of these dopants to the perovskite films to these inactive areas of transport. And the result is such, so we've seen a clear effect of doping, that we have a good enhancement of conductivity up to maximum order of 2 for these 2D perovskites via bulk doping, we believe, of the reasons as the following. So we found it interesting that by using different solvent, and therefore the different size of the solvents, as well as their solubility to the organic spaces, this is representing the peak for layer distance. So layer spacing. So people can call it lamella spacing, where the distance between the layers of n equals 1 perovskite, which is represented here, 002, that peak is actually shifting depending on what kind of solvents that you're using. So by using these DCB or DCM solvent, you're able to shift these peaks for the 2D perovskites, which is representing the fact that you're expanding these lamella. So you're expanding these layer spacing so that you are actually allowing in more solvent molecules, such that you are able to allow in more dopants, which is what we expect. And therefore, the conductivity increase was the largest for DCM. And we were actually surprised that this was actually happening in bulk scale through the bulk film, which we confirmed from the time of flight SIMS, as well as the solid state NMR with JJ, who did an amazing work on 2D correlation of looking at these dopants, as well as their structural correlation with either the lead or the spacer elements. In this case, it was 1H proton. And when we looked at the correlation between 1H of these and also 1H on the dopants, they seem to be highly correlated, which meant that these molecules were lying in the proximity areas of the spaces. So that, I think, was how we came to believe that this was bulk doping. And as I mentioned, the solubility as well as the effective solvent sites had a good effect as well. So we'd like to call this a Goldilocks zone, where DCM, so in this direction, the doping effect was the largest because it has the smallest solvent molecule size, as well as the right solubility of not dissolving perovskites. Believe me, and perovskites dissolve very easily. And also allowing to dissolve the dopants themselves. So that sums up. And if I just may give you 1 minute, 2 minutes for what we work on 3D perovskites these days. So this was a p-type dopant, as I mentioned, the molecular dopant. And we came to question, okay, how can we extend this to 3D perovskites? And also, is there a way to n-type dope these materials? And from molecules, it was very difficult, and therefore we moved on to something else, which I will talk about. So bulk doping in 3D perovskites. So if I give you the challenges again, the idea of doping perovskites is suffering from all these different challenges, but mostly the anti-doping and the doping efficiency. So anti-doping is difficult because you have this lead 2 plus in perovskites. So this divalent metal cation in perovskites, if you reduce it, then in the end, you're going to create lead 0. And lead 0 is very hard to reversibly, let's say, oxidize. So once you reduce to lead 0 plus, then they may not be coming back. So anti-doping is quite difficult. Then the question is, okay, how can we break the limits for the doping by inducing N-type as well as breaking the doping efficiency limit for the current method? And we seem to have a good idea of how to do that by thermally evaporating these special types of dopants, for which we see this large increase in the conductivity up to 5 orders of magnitude by depending on the different dopant thickness. And this is controllable over a wide range, so it has a good trait in terms of controllability. And we see that this is bulk doping by top sims as well as doing the top contact and bottom contact. So what we're hoping to do is continue by preparing this paper to understand the mechanism, which is not so clear, as well as use it for device applications. So in the last few minutes, I will give you some outlines for what we'd like to do. So I've shown you different types of doping in perovskites. What we're exploring is also the electrochemical doping type of sort. So we are interested in extending the range of types of doping that we are able to achieve for this perovskites material in order to dope the undopable, let's say. As I mentioned, anti-doping is very difficult, and also you're restricted by the number of elements that you can use. By introducing these extra concepts, you may be able to break the efficiency limit for doping. And also, in the end, you'd like to use these for device applications, such as optoelectronic devices, where the perovskite is the most promising. Also, the rising emerging device application for electronic devices, perovskite transistors, which we also heavily work on. So innovative doping solutions will be hopefully come up. So by that, I'd like to thank mainly Yongjin, who's been a great student, my actually first PhD student, who's led some of the research works in my lab. We're currently a medium-sized group with 2 postdocs, 6 PhDs, and some undergraduate interns. And I thank all my collaborators for collaborating on these projects. And also, I'd like to thank other panel members, including Alice, as well as the audience for your kind attention. Thank you.
Okay, yeah, we got a doping master. Okay, so you really interesting work and feel really good. So yeah, let's move on to the panel discussion. Jump to that panelist. Yes, so nice in different topics. Oh, we're jumping. So we have 2 beautiful panelists here. First, Jiang Ying. Yeah, Dr. Jiang Ying, they are Hong Kong University of Science and Technology, 广州。而且嘉英问下课，发生更加什么 first campus set up, right? Yeah, at the moment, yeah, you that Jia Ying will her PhD technology and is a company physics Diane, welcome. Yeah. We have another panelist is Mike Price. Crystal. Mike has a very qualified experience. All at the New Zealand, get started and part of the countries, right? And after get PhD, got to an NGO. Um, yeah, NGO, so something helping developing countries. And then he back to academy 2018. Victory to as a welcome. Yeah. So let's welcome everyone come to the stage. On the stage session. Normally our discussion start from Jiaying.
Okay, thank you for your kind introduction, Alex. I think most question from me is for Philip. Okay, so in your introduction, you mentioned that the large energy offset, and that is kind of the main voltage loss for organic solar cell. But if I remember correctly, the voltage loss doesn't really go linearly when we reduce the offset. Do you have any comment on that?
Yes, thanks, Jiaying. So, you know, I think what you just said is perfectly true, and that is, when we look at the efficient systems, right? So the ones that have above 15% efficiency, so at least 14%, right? And essentially, these are all based on the non-fluorine systems. And when we try to measure this so-called energy offset, and this is commonly done by people, we would do like CV measurements in the two materials separately. We would get the HOMO and LUMO levels, and we kind of just assume that the HOMO and the LUMO offset represents this energy offset in the systems, right? And obviously, if you do try to draw a relationship between this offset and the device VOC, then most likely you would not get a very clear-cut trend, right? So, about this, I think it comes to two levels. The first point is that we simply cannot fully trust the so-called energy offset that we determine from CV measurements of the two materials separately, right? The reason is because when they come together, when the two materials come together, they would form intermolecular interactions, right? And basically, we all know that intermolecular interactions, aggregates, etc., they would basically change the energetic levels, right? Not to mention, any energy, bending, etc., at the interfaces. So this is the first point. I think even now, I don't think we have a very good way of really measuring this so-called energy offset at a definite level, right, of the donor-acceptor interface. The second point is that I think if you look at some of the more traditional systems, it's all polymer, like traditional all polymer systems like FABT, PFB, and even some of those PCBM systems where you do have a large offset, then you can clearly fit a relationship between the energy offset that you measure mostly from CV measurements and the VOC, right? Because those we can measure easily, right? But now we have very small offset, and basically we don't really have a good way of measuring it, and therefore we do not see this trend. So I do believe that is probably what's going on, and also because now, as I explained in my talk, probably the energy offset is already very small. That in all the efficient systems, we don't really have a large offset anyway.
Yeah, indeed. It's fair that so we don't have a very good techniques now to measure the interaction between the donor and acceptor. Just follow up these questions. So yes, now we do have a very small energy offset, but then the question is what's the driving force for charge separation? Yeah, you did mention that the exon binding energy is large, and we do need some driving force to separate them. But what is now? I mean, they are if the below 100 milli-electron volt, that's already smaller than the binding energy. Do you have any thoughts on that?
Yeah. Again, right. This is a really good question, and for sure, there's still a lot of things we need to do more deepen our understanding, right? Now, from what I personally believe, right, is that currently, all these systems, they are very small offsets. Essentially, the energy offset doesn't really play a major role in helping the electron separate from or electron separate from the hole, right? But instead, because of this small energy offset and the way that we're engineering this offset, this molecular interface, such that there's very low amounts of energetic disorder, where as long as your electron and hole pair, right, as long as the exciton lives long enough, right, meaning that they have relatively weak vibronic interaction with the structure, so that the lifetime is relatively long, then basically they can afford to wait until thermal activation comes in, which we know but from our experiments at room temperature that this happens at tens of picoseconds, right? So basically the key is that we have found a molecular engineering way to really get rid of energetic traps, if you like, or defects, right, at the interface, so that these electrons and holes, they can kind of live for long enough, tens of picoseconds, so that when thermal energy kicks in, which remember gives us 25 milli-electron volts, right? But over time, right, that would also accumulate, right? So over time, that can allow the charges to separate. And we know from our experiments, this roughly takes a few tens of picoseconds and completes at about 100 picoseconds.
Yeah, I guess that's very difficult to manipulate the steady state disorder.
Yeah, that is absolutely right. And that is also the reason why it took us so long, right? And to be fair, these are really complex material systems. As you just mentioned, right? We don't even have a good way to measure the energetic offset at the interface, right? This is very different to traditional inorganic devices, right? So I think this is probably the reason why it really took us, right, the whole community, driven by chemists, right, through empirical modifications, right, of the molecules, and somehow, right, we managed to find a really good recipe, and then now we're sort of working a bit backwards, right, to try to understand the physics behind these top performance devices, which will then hopefully give us the provide us with the design guidelines, right, to develop even better materials with higher performances.
Yeah. Okay. Do you have enough time to ask more?
Can we move save next speakers?
Okay.
Then you come back again.
Okay. All right.
Okay, Mike. Yeah, Mike, are you ready?
Yeah, thanks. I would love to speak with Philip and Jia about charge generation for the next couple of hours. It's really great topic. But I'll ask some questions to Emrys, because I thought they were really interesting, fascinating topics and quite important as well. So Emrys, your new quantum information systems, you measured them. You're able to read out these spin states in solution and in the solid state as well. Can I ask a bit more about how the molecules were prepared as a solid?
Yeah. So those systems I was talking about at the end of the talk. So we are studying them in disordered films. So we take these materials and we spin them in PMMA, so polymethyl methacrylate, and we made some, quite basically, when you have a material and you want to make a film, it's the kind of first thing you try. So they were disordered films, and so when we were looking at trying to study their magnetic response with light, we studied them at room temperature and also at 4 Kelvin. So actually being able to put them into films, which is a very obvious thing for the optoelectronics community. But actually, people who are kind of working with molecules as quantum systems had always kind of studied them in solution before. So that was actually quite an easy way for us to kind of move things forward, because it meant that we weren't limited by when is the solution not a solution but a frozen solution anymore. Yeah, hopefully that gives you a bit more info.
Yeah, have you started looking at, because I think obviously in the quantum community, people are very much into pushing, certain types of chromophores in a very ordered way, growing them inside, ordered crystals of anthracene and stuff like that. Are you able to look at those types of techniques, or?
Yeah, so the results that we had there were bulk ensemble techniques. So something that would be really important is to take some of that phenomena down to the sort of single molecule or single qubit level. So we have tried some experiments with quantum optics groups, try and make this work. But unfortunately, one of our limitations at the moment is it's called the optical ODMR contrast, or basically the sensitivity contrast for when you apply these microwaves to your system and then you try to induce spin transitions, what kind of signal level you get out. And at the moment, our contrast, we can pick it out in the ensemble. It's about 0.1% sensitivity, whereas to kind of make things work, you want to kind of calibrate yourself to what people who work with nitrogen vacancy diamond do. They have about 10% contrast. So there's a few orders of magnitude to play with. So something that we're trying to work out on the molecular level is how do you get better contrast? And we think that's got something to do with being more selective in terms of your spin-orbit coupling transitions between the different sublevels of your system. So we're at the moment actually mainly focusing on trying to get better distinguishing spin-orbit coupling properties within these materials. But yeah, something that we'd like to do is to try and to build up these systems so that it's not just kind of one type of qubit in your pot, basically. Yeah.
Amazing. It's incredible. It's really exciting, I think. We'll come back, but maybe I'll ask Key one question and then we can.
Right.
Yeah.
Good to see you again.
Great talk.
Yes, thank you.
It's so important, doping. As someone, because you've looked at it from a lot of different perspectives, like what like a general question, what do you think would be the most industrially relevant form of doping for say, and is it
Great
different for perovskites compared to organics? Or
great question. So Mike again, and thank you all for opportunity to talk to Mike again. So organic semiconductors, from my experience, since they are already van der Waals bonded, I mean, if you talk about small molecules as well as conjugate polymers, since they're van der Waals bonded already, I don't think there is a great binding force or binding energy to have implanted dopants in polymers, unless you physically block them, unless you create this crosslinkers, for example, to physically blockade the dopant motion in conjugated polymers. And from my experience in doping organics, it suffers greatly from the diffusion of the dopants. And therefore, it can be very thermally unstable, blending these dopants, small molecule dopant, with polymers for solar cells, for example, when you use it for heterojunctions. So the idea there is that achieving thermally stable doping will need some kind of, I think, physical barriers, either in the form of crosslinkers that should be used with not the dopants. And unless you do that, you are left with diffusive doping, which is a technique that you use for silicon as well. But more stable form is to use ion implantation doping, where you can specifically design the doping profile in silicons. And the situation is not so different for 3,5s, gallium nitrides as well, where you have these ways to post-process dope, but at the same time, you're playing with different systems because these are ionically bonded now, unlike silicon. So you also have a bit of a problem in introducing these dopants without self-compensation effects. So there, I think also the challenge is, although for gallium nitride it's been solved, to introduce not just during synthesis doping, but also post-growth doping. So that's also a challenge. For perovskites, I've talked about lots of different things, but molecular doping probably, from the same reason, the binding energy is so small, it's only Fiddle's option, and therefore for making industry applicable, it's going to be very difficult. So we need to really play around with the restricted structure. So by replacing some good ions as dopants to perovskites, but also dealing with the fact that perovskites, the ionic motion is really large. You need to think about passivating defect sites, as well as introducing extra, replacing heterovalent atoms. So the challenge. So I'd like to mention to you that challenge is multitude. There are multitude of challenges, but that's my current opinion on what would be the optimal doping for these range of different materials. But I would say there's no one solution, but it really depends on what kind of systems you're talking about. So I know you're interested in organics, and maybe we can talk a little bit about that later. But there, I think you would also get challenged with the fact that these dopants, they tend to aggregate or diffuse, which is interesting, which links back to Philip's talk, right, on thermodynamic stability of this biphase materials. Sorry, I talked too much.
That's great.
It was a
No,
great
it's
question.
amazing answer.
Thank you.
Yeah, great.
Yeah.
Okay, maybe I follow up to the doping master. Yeah. Actually, you really talk, and I was like electronics doping population process. I think in the last slide you said that was bulk doping. Yeah, so I didn't quite get it.
Okay. Oh, thank you so much. Thank you so much, Alice. Alice, if you've worked in microelectronics, you should be the doping master. But yeah, so we're trying to follow up with what microelectronics community has achieved. And it's very established in silicon, for example, how to do that. Also gallium arsenide, I think a number of people, it's very established. So bulk doping is basically from the molecular doping perspective. As I mentioned, these molecules, they tend to sit at the interfaces. And therefore, in order to induce bulk doping, which is not only on the surface, but also including the dopants within the bulk film of the semiconductor, just like how with ion implantation doping, you're able to select a right depth profile for pushing in the dopants further into the film of the bulk, which is very difficult for organics, as well as for perovskites, because it's limited by the structural stability. So what I'm interested in is trying to extend this range of doping such that via inducing dopants into the bulk and making it stable, induce a large range of conductivity as well as doping as possible for device applications.
Okay,
I don't know
that's
if it
very
helped.
clear. Yeah. I may I may challenge you for the depths about that about depths in micrometer, nanometer, and see.
Yeah, that's true. So yeah, I mean, we are still dealing with thin films, and therefore, if we talk about bulk crystals, which tend to be micron size, I don't think we have penetration into the micron thin. So yes, it's only limited to thin film so far. Yeah, thank you so much. Yes,
Okay, I'll try to clarify this. Yeah, where does Jiaying have questions? Mute.
Unmute. Okay, now I'll unmute myself. So for Philip, I have a technical questions, or maybe for Evans. So I mean, anyway, so for Philip first. So how do you push CT state? I mean, you mentioned that it's not easy to push the CT. You may push singlet or you may push polarized, but how do you selectively push CT?
Yeah, that's a really good question, right? I think the way to look at it is, we have excitons and then we have polarons, right? And
Mhm.
CT states and free charges, they're both polarons.
Mm.
So what we found was that, at least for the systems that we looked at, was that the excitons and polarons have very different absorption profiles. Because of the excited state absorption are very different between these two species. Because of that, right? So when we inject the push energy, right, we selectively set the energy of the push pulse to be only overlapping with the polaron absorption, but not the exciton absorption. And we simply did a lot of different push energies. We pushed both excitons, and polarons, and then also both of them, and we can see very different observations. So then, it took us a bit of time, but eventually we found an energy where basically we only excite the polarons, but the excitons are not, they give us a very different results. So by doing all these control measurements, we were able to differentiate when we're exciting or pushing the excitons or pushing the CT states.
Okay, thank you, Philip. Maybe for Evans. Yeah, I'm very interested in this like molecular spin electronics. Yeah, but also from experimental point of view, how can you see those how easy we can see those doublet and quartet? For example, for doing tasks, we are talking about for polaron, the to see polaron, the delta OD is about 10 to minus 3, right? And how easy we can see those like doublet and quartet, from optical measurements.
Yeah, it's a good question. So it's I'll answer it in the quartet one is an interesting one because the quartet systems that we study are made up of triplet excitons and ground state radicals. And actually, when you do the TAS experiment, you can't distinguish a quartet state like that from a triplet exciton itself. So what you really need is to do these magnetic resonance experiments. And these electron paramagnetic resonance experiments, we can actually look at different transitions within the spin sublevel. So for example, a quartet state has got transitions that take you from a -3/2 state, not only to a -half state, but also to a +half state, and to a +3/2 state. So there are actually fingerprints in the electron paramagnetic resonance that can tell you whether you've got a quartet state in there. So something that kind of troubled me when I started working with these systems was how do I prove that the emissive state is a doublet state? And that's actually been part of the motivation for the last part of the talk that I was talking about, where I was trying to understand if I have a system that is emitting through doublet states, what can I do to prove that emissive state has got more than one sublevel and that it's not a singlet sublevel? So that's why we've been motivated to look at these magnetic photoluminescence experiments, because the plus minus half sublevel of the doublet state interacts differently with the rest of the manifold, as opposed to if you just had a singlet emitter. So it's a great question and something that's troubled me for many years now. we're kind of continuing to work on it.
Okay, thank you. Okay, Alex, I'm done.
Okay, yeah. So I came to the last question. Yeah, I take advantage. Because I realized that all of you study, right? Yeah. Some level mates, right? Some friends and some from us alumni. And I realized that all of you part of the world studying. So yeah, that makes us like Nazis, right? Yeah, a lot of cultures, Nazis, a lot of things. So I may try to. Yeah. What's your feeling? Study like especially like travel around the world, different cultures like you, New Zealand, US, and Australia.
Yeah, that's a great question. Obviously, the institutions reflect the national culture somewhat. So I would say it was somewhat more relaxed working in Wellington in New Zealand than it is here in Bristol. I'm not allowed to wear my like sandals and shorts and abs here, which is fair enough. But you know, it's different even across the UK. It's different in Bristol than it is in Cambridge, as I'm sure it's different in Swansea. And the US was also very, very different, very eye-opening. But I was only an undergraduate student there, so didn't fully experience the culture of working in the research environment there. But certainly the lecture styles I found across the world are very different. And each one has its own pluses and minuses. So it's probably too diplomatic an answer for you, but
I mean,
that's what I'll say.
Does it shape you a lot? Yeah.
Yeah.
Okay. Yeah. Interesting. So for Emrys, you study in Oxford, study in Cambridge, like like I'm like a competitor. So what's your feeling and top unit cultures?
I think they're almost exactly the same. So, I think the kind of unusual thing about Oxford and Cambridge is there are big universities, but split up into small universities. So they have this college system, which is very nice. So it means that often you get quite a personal experience as an undergraduate or a postgraduate student. But yeah, they're both great places to study for sure.
That like the castles, Harry Potter, like you. So yeah. Oh, Kang, you study. I think.
That's true.
Yeah.
Yes. So yeah, about 15 years. Yes.
Half of life.
Exactly. All my 20s were spent in UK. So
Wow, okay. The big benefit.
oh yeah, definitely. And also, I would say, as I've thanked you for bringing us together, I think it's also about the people who are doing excellent works in their field, not just in research, but I've also met many people who are now working in industry. So this diverse range of talents, as well as the culture that I was exposed to in Cambridge, especially, I'm really treasuring. Also back in Korea, I'm meeting so many Cantabrigian, so Cambridge alumni. I think also the fact that Emrys, as Emrys mentioned, having college system really helps in bringing us to different disciplines together and trying to have something more refreshing rather than just talking to physicists all the time. So yeah, something like that. I was really, I think, I really grew in that environment, and I have that diverse background that I can think of now. So yeah, so that's, I think, something that I'm really grateful for the UK experience. Sorry, it was too constructive and nothing exciting, but yeah.
It's okay. It's the culture, not the people. Yeah. So yeah, Jiayin as a super lady, you will travel. This is everything, and now back to benefit.
Yeah, I very much agree with Kang that back in UK, I was exposed to like a great diversity of people from many nationality and also from, different background. Not like what I did. I did undergraduate in mainland, and most time I'm just talking with very similar, background students. But in UK, yeah, I did met lot of different people, and also I think in UK seems they have a more work-life balance and allow me to think a lot. But here in China, I think also in South Korea, it's more pressure, right? Also peer pressure. I think, yeah, but
Go to
yeah, that's right. But of course, I feel like I was pushed to go forward. But in UK, I feel very like privileged that I'm thinking I need to move forward. I think that's something I feel different when I come back to mainland. And also in terms of research, of course, now I'm in a very American or US style university. But still, in terms of the survive in mainland China, we need to apply funding. And the funding here, I feel like it's more like application oriented because it's competitive funding. We have to demonstrate we will make enough impact within 5 years. And yeah, those I think I feel it's different to what it is in UK. So UK, there's some more, I feel like more curious driven research, maybe finding opportunities.
They should also have pressure for fundings, right?
I think for US also very competitive for funding as well. Yeah.
But now we have one can answer your questions because Philip was the one full of fundings. Yeah, Philip, how you found out you got so successful got funding?
Well, for sure, I'm definitely not the most successful, very far from
Why?
that. But I mean, I'm pretty sure we are all experiencing the same situation, right? I mean, as young faculties, independent PIs, right? Then obviously, yeah, well, we need to continuously seek research funding. I think at the same time, that again, try to look at it from the positive side of things, right? It also gives us a motivation and drives us to try to really think carefully about what we want to do. But I completely agree with you, right? Obviously, we need to find a balance between like, just impact and fundamental science, right? Probably we need to really try to satisfy both at the same time, and obviously that is very challenging.
I think that especially for weapon positive, not just for publication, the paper, nothing. Yeah. So I think this really is something, especially for young generation. So dedicate all the questions like. Otherwise, but I can feel that I see you have some really deep insight. So dropping like a questions, curious or really excited about talk and can excited about. That's the best part, especially young generation found your exciting. That's more else. So okay, yeah, I think for the panel we has a lot, maybe something more than a normal panel. So cool. Let's move close the panel. Let me our part. Actually, I think today was a big day because this was years ago. So yeah, you see that this was my year for pick out the ICANN's talks and 2020 17. That day was I remember clearly it was day, the raining day. So I stayed there, but I feeling I must cheer myself. So yeah, we got this talk kick out. We invited speakers. The first one, yeah, this was the first from the ICANN's talks. John Rogers was Xuan He from MIT. So April 17 was a time to get on the stage. Everyone's so excited. Let's see how they look like. Yeah, this was John Rogers patient. The first one, he says that tell you how the high tech changes the world. So yeah, that's how exactly ICANN want to do. Tell the world how the high technology is happening now. Well, world. So our number one speaker is John Rogers. All of you know him. Successful and deliver wonderful talk. People's online that is like this. So yeah, it looks like this. It's very exciting. Pick out, but no one believe. 4 years later, this became the nine talks of science. Everything starts from and then become and big. Especially like just now we talk about that young scientists struggle and I can add some struggle very very much that time, but now it's getting much better. I think all of you will be much better in that. So the talks they have a angle work on platform act the other on page. Yeah. This was talks to have the uh have the people part of the world. Nice. Yeah, see have a big yeah, we have a Martin Kinney. Yeah, so have Paulo with France, we have a China, we have Lan from India, we have a have Paul from LA, UCLA, with Alice here. So this team running every week. So some of them by this and everyone are the last 4 years we have 110 regions cover all of them. Have 105 of 59 days. We have a big number. I'm glad to tell all of you we have over 1,000 lines. Yeah, getting a one. So was have some of the picture. I'll have a big one with all of you, everyone on that. So this was my talks now is running like because we have a worse scientists qualified to apply for this. We have an on-site in the lab. Other have a summit. I'll go to Davos. Have a fund of young people. Davos summit will be July 11th, 12th. So yeah, the topic will cover the science, technology, investment, management. Short for it's time. So it's time to go Davos. To get everyone to go there, will be our first party. Hopefully have more fun, get more ideas, some idea. Welcome all of you to there. And next week, sorry. Just now, the question part, the talk part of question part, I think qualified. Many answer many questions. Yeah, many questions and answer very good. So call it available. Now you have your IE cards. Congratulations.
Thank you very much, Alice.
Thanks for organizing. And okay, let's go. How about Kang? Kang, did you answer questions right? Okay, yeah. So yeah, they think you're right. Okay, now you got the certificate. Okay, yeah.
Thanks so much. 谢谢你，谢谢你。
How about Evans? Okay, yeah. So Evan, yeah, you got 2 because you answer questions and use comments. Okay, that's okay. Yeah, next week we're going to have the session is about skin and then we'll have a group young scientists China have that like this and base us our talks. Welcome everyone to enjoy and science and technology network. Thank you very much.先生、女士们、亲爱的朋友们，欢迎大家来参加我们的 ICANX 达沃斯科学峰会。那今年是第1次 ICANX 会组织大家一起在瑞士的达沃斯进行线下的聚会。我们有6个主要的议题。第1个是创新 innovation， 第2个是科学 science， 第3个是 technology 我们的技术，第4个是 investment 投资，第5个是 management 管理，第6个是 entrepreneurship 创业。所以它结合起来就是 It's time 是时候了，是时候让我们去达沃斯听这些非常 给我们启发的关于未来的这些报告。在达沃斯，我们会有3个非常重要的论坛，一个是诺贝尔奖论坛，我们会邀请诺贝尔奖获得者来跟我们谈科学的未来，我们会邀请世界科学院的院长来跟我们谈世界科学技术发展的未来。那我们会邀请大学校长来参加我们的世界大学校长论坛，来跟我们谈关于教育的创新教育的这样的一个未来。同时呢，在达沃斯呢，我们也会邀请各行各业的这样的一个非常重要的领袖人物、领军人物来跟我们分享他们的所思所想，他们对未来的思考。那我们也会邀请非常多的各行各业的精英来跟我们分享他最精华的这样的一个思想。那当然了，达沃斯这个舞台也不只是给这些大牛们展示的舞台，也是我们来展示的这样一个舞台。所以如果你有好的故事、好的思想、好的技术、好的思考来进行分享，那也欢迎你再来线上投稿。所以我们的截止时间是4月1号，大家还有1个月的时间来准备好你的发言，希望分享给全世界的。所以欢迎你在线提供你的资料。那我们也希望你成为这个舞台上的明星。那在达沃斯呢，我们设了3个奖，第一个是针对大学生的，你是创新创业的最牛的大学生，那你来申请我们的创新奖。如果你是一个毕业10年以内，现在正在从事独立科研工作的科学家，那你来申请我们的青年科学家奖。如果你是一个创业者，你成立了你的公司还不到5年的时间，已经发展得非常好，那请你来申请我们的创业奖。所以所有的奖项申请的时间截止都是4月1号。那欢迎大家在线提供这样的一些资料，那我们也会给大家非常多的这样的机会，成为舞台上最亮的星。那是时候来我们大家一起把科学推向未来，推向世界。那这个呢，是我们在达沃斯的非常重要的合作伙伴。我也希望你成为我们的合作伙伴，我们一起来推动世界的发展。那现在达沃斯论坛已经开始注册了，所以各位朋友、各位好朋友们，请你们开始尽快注册吧。我们相聚在达沃斯，我们一起